So welcome to lecture 2 of machine learning methods for atmosphere, ocean, and climate science. And I would like to thank Jim, Ashwin, and ICTS again for organizing this so that we are able to discuss this together. So as discussed yesterday, in this lecture today, we will start by implementing our own neural network using Python's PyTorch library. And yeah, let's just get right into it. Let me just discuss a bit about the structure of the PyTorch library and so on before we actually go on and start with the coding. So as you can see in this plot here, the PyTorch library is a collection of many different modules like the Autograd module, the NN module, the Optim module, the utility module, and they all serve different purposes. So for instance, the Autograd module takes care of the backpropagation algorithm that we looked at yesterday. So you don't have to worry about it. The NN module provides you all the necessary classes and the functions to implement your neural net just create all the functions and the different layers of the neural net and start the training process. The optimizer contains a set of optimizer definitions that you can use to make the weight updates in your neural net. And the utility module helps you manage your data by creating batches out of your data, creating something called as mini batches that you can use for training, implement random shuffling of your data and all that. So hopefully all of you were able to install, and I'm sorry if you were not able to install PyTorch, but I hope, for some reason, if you were not able to install it, you are able to follow the discussion today. Just let me know if you have any questions, okay? So as mentioned here, you can import all these modules and the library using simple commands like import torch that loads the whole library and the namespaces associated with it. And if you have to load specific namespaces for torch.nn module, you can use proxies by importing torch.nn as nn, just like you do for NumPy, import NumPy as np. And similarly for optimizer, for the optimizer module, you can use torch.optim as optim, and similarly for utilities, right? So, I mean, if you just go to the PyTorch website, I think that's a pretty comprehensive description. It provides a pretty comprehensive description of all the models and functions. So yeah, I mean, it has a huge list of all the convolution layers, padding layers, activation functions that you can actually use to build your neural network. So you can go through it, whenever you're creating your own neural network, just go through it for reference. And I mean, it gives you all the list of parameters and arguments to a function that you would need. So we didn't talk a lot about activation functions yesterday, but we'll briefly talk about them today. We briefly looked at the sigmoid function yesterday. So PyTorch allows you to have different kinds of activation functions, like the ones shown here. The sigmoid one and this. So there's the sigmoid function, there's the tan h function, and if you look at them, you compare the figures, they look quite similar in a sense that they have two asymptotes. One so for sigmoid, it's at it's at minus infinity, and it asymptotes to 0 at minus infinity, and it asymptotes to 1 at infinity. And similarly for tan it has asymptotes at -1. It asymptotes to -1 and +1, right? So usually these functions are used for binary or multi-class classification problems because, just imagine you have the affine transformation. You apply the affine transformation on your inputs, and then this maps everything onto either of the two legs of the function. So it's kind of projecting it into two different clusters, projecting all your data into two different clusters. Whatever is projected in this region is kind of shaky, but then, usually you can get a nice classification on simpler problems by using these functions. Similarly, there's the rectified linear unit function, which is called ReLU in short. And the definition of this function is quite simple in a sense that it's piecewise linear, if anything, but it works pretty well in practice. So the definition is given here. But then the main reason why ReLU is popular is because of the derivative. If you remember the derivations yesterday, we looked at, we encountered a term sigma prime, that is the derivative of the activation function. And the more of these derivatives you have, the more error will accumulate if this factor is greater than 1. So with ReLU, you don't have to worry about that because the derivative is for half of the real number line, it's 1, and for the other half, it's 0. The only caveat is that you're throwing away half of your samples if they are negative. But then, tests in general literature suggest that ReLU works great. Similarly, the softmax. The softmax activation function is mostly used for when you're dealing with probabilities, large language models, and so on. What it essentially does, it takes a set of random any numbers of any size, and then it converts them to between 0 and 1. And essentially, it's converting them into a set of probabilities, and you pass Z1, Z2, Z5 as the argument. It returns y1 and so on till y5, and then the sum of yi's is equal to 1, which is what you would want from your probability density function. So now similarly, there's different kind of loss functions. There's the L1 loss function, which if you have the prediction and the truth, you can compute the L1 norm of the vectors, and that gives you the L1 loss. Similarly, there's a function for in the NN module for computing the L2 norm. And then there's this function called as the cross entropy function, which is also called the softmax function because softmax loss function, because it's similar in structure to the softmax activation we saw, in the sense that it's the log of the exponential of at a given node divided by the sum of exponential for all the nodes, and it's a weighted average. Now, finally, there's this KL divergence function, which is usually used when you're dealing with probability distributions, like if you're applying variational autoencoders or transformers there. You're working with probabilities, and this is used to quantify the difference between two probability distributions. So, I mean, if you have some background in information theory, you would know that this expression right here is called the Shannon entropy. So this whole term kind of computes how different the entropy of the two probability distributions are. Now, lastly, there's the optimizers. You can choose from different optimizers. So the most basic optimizer that we also kind of looked at yesterday is the stochastic gradient descent, which was introduced by Cauchy back in the 1840s. And you can this is the command to initialize this function. Now, the most basic, the vanilla definition of the stochastic gradient is what's shown in this line here. You have a learning rate, you have the gradient at time step t, and then you have weights at time step t, and then you use this information to compute the next parametric update. However, if you look at the next two lines, there's something called as the momentum. So you can have momentum in your optimizers, which is given by the momentum coefficient is beta here. So what you're doing is you're making something similar of an update as you were before, but then now you're updating with something, with another value, which is Vt, which is the gradient plus beta times the previous value of Vt. I mean, I can use this one if it's, yeah, that's fine. Yeah. So yeah, this. Thank you. Okay, yeah. So basically, these two equations define stochastic gradient, but with momentum. Now, there have been some recent developments in the theory of optimization, and there have been some new optimizers that kind of make use of multidimensional calculus to create better update steps. So there's this. So in 2011, a new optimizer called ADAGRAD was introduced. So then the good thing about this ADAGRAD optimizer is that instead of a fixed learning rate, alpha, it uses a variable learning rate, which changes with every step. So it uses the trace of the gradient matrix, and then it adds a small perturbation epsilon. And so, when you're initializing the optimizer, you'll just set alpha, and it can, and you can, like, that's the maximum learning rate. And then you can also, it will vary scale alpha accordingly. And then it will use the gradient, multiply that with the gradient, and make the parametric updates. Now, similarly, there's RMS prop. 1 year later, the RMS prop was published, and actually, I think it's never published, but it was introduced. Now, what I'm getting here is that RMS prop uses a learning rate as well, a variable learning rate as well. But then at the same time, it uses momentum as well, similar to the gradient descent with momentum. Okay. Now, more recently, the most recent in this list is the Adam optimizer, which is again one of the most popularly used optimizers. And the good thing about this is it combines ideas from all these three optimizers. That is, it makes a linear parametric update using the gradient. Excuse me. And then it uses a variable learning rate. And then, so it's not just this one equation. There's a set of 5 equations that Adam uses. And then it uses 2 momentum parameters. So it brings everything together to have momentum, a variable learning rate, and oh, what's the third thing? Oh yeah, so momentum, and then adaptive learning rates, and then like this nonlinear combination of the gradient and the velocity. So what optimizer you choose for your problem can again depend on the problem, but then the thing you should be aware of is that so okay, this image right here shows the performance of 6 different optimizers initialized with identical weights, and then you can see that the way they're defined, with momentum, without momentum, adaptive learning rate or not, that significantly affects the parameter space they explore while trying to find the local optimal minima or maxima. So you see the SGD, the red curve here. I mean, it moves very slowly because it does not have that momentum added to it. And on the other hand, there are some optimizers that kind of just break away from the bunch, but then again, they return and finally give you the optimal maxima or minima. So the main point here is that all these tricks or techniques help you prevent stagnation while finding the optimal parameters. In a sense that if you again look at this bottom figure here, you see that stochastic gradient is stuck at the saddle point here because it does not have momentum. It doesn't have that kick to prevent it or to add that noise and to kind of compel it to go in some other directions. And it just kind of gets stuck there, while the more advanced optimizers quickly realize that it's a saddle point and they go in the direction where the loss is minimized. Now, quickly, again, as I said, you don't have to deal with the Autograd module of PyTorch, but then it's good to have a good broad sense of what it's doing. So Autograd essentially, as we discussed, it helps you maintain or optimally compute the gradient of the loss function with respect to the weights. But it does so by maintaining a graph of the different variables and how they're connected. So just like in NumPy, you have arrays. Similarly, in Torch, you have tensors. Okay, so the arrays in the n-dimensional arrays in Torch are called tensors. And then whenever you define a tensor, it creates a node in this graph. So for instance, you have 2 variables A and B, and then they're used to, they have values 2 and 3, and they're multiplied to get another variable C. Now, if you want to take the derivative of C with respect to A and B, you just need to execute this function C.backward in PyTorch. And then that will again backtrack to all the variables that contributed to getting the value of C. And then it will automatically take the derivative and it will store the derivative here. So grad, so partial C, partial A would be B. So, and that's 3 because the value of B is 3. Now the catch is that by default, there's this parameter that's called requires grad. And this is set to true for any tensor. But then if you shut it off, it automatically is detached from the graph and it will not contribute to any gradient calculation. So that's why you see the gradient, that partial C, partial B as none here because the required grad is false. Don't worry about all this, okay? I just, you can just skimming through this, but you can go through it later as well. So the set of commands that help you do this is, you compute the loss and then you execute the command loss.backward. It sends the gradient to all the nodes that help you compute the loss, that is the weights of the model. And then you call in the optimizer and then you ask it to step and make the next parametric update for the model Okay, so now there's a natural question: why PyTorch? There are other coding libraries like TensorFlow, Keras, Scikit-learn. Why PyTorch? I don't have a good answer to this, but the convention is that PyTorch is easier to learn for researchers. So I didn't really bother with TensorFlow, and especially when I started using, I started with machine learning. PyTorch was gaining popularity, and now it has a big community of developers and so on. So that's why I use PyTorch. But then many of the recent, impressive transformer models are also created in PyTorch. So, just putting it out there. But this is not to say that TensorFlow is better than TensorFlow is not good enough or anything. Even now in industry for deploying ML models on a large scale, people prefer TensorFlow. Now, just a couple of slides before we start with the notebook. The training process. Now, there's a couple of ways to train your model. The first is, suppose you have 10,000 samples, for instance, of your data, right? So you have 10,000 inputs, and then you have corresponding 10,000 outputs. One way is just to input all the data together. So at every iteration of the model training, you use all the data to make one parametric update, like the one optimizer step, okay? The other alternative, which is the other end of the spectrum, is that for every iteration, you use just one sample, and then you iterate through all these 10,000 samples and make 10,000 parametric updates for one iteration. So the benefit of this is you add certain noise, because the more samples you have, the more means, the more samples you take to compute the loss, the more smoother your transition is for each iteration. But then this also increases the chance of getting stuck in those local minimas. So this stochasticity that you see as red arrows here, this noise, helps you get over those local minimas and approach a global maxima or global minima. Now, another benefit of this is that if you're training your model on GPUs have limited memory. So if you have huge data sets, then it's not possible to load the whole data set into the GPU memory and then train on the GPU. So using these small batches, as they're called, you overcome that problem. Now, of course, if you have just one sample per model update, it's slow. So what is usually done is the whole data set is divided into mini batches, not just single samples, but something like 20 or 30 samples or 40 samples. So if you have 10,000 samples, you create mini batches of 40. So you'll have 250 mini batches of size 40 each, and then you use them to update your parameters. So batch 40. So for every training iteration, for every training epoch, you will have 250 parameter updates, not 10,000, not one. Okay. Now, I don't know how many of you have heard of Jan LeCun here. Okay, he's one of those considered one of the fathers of machine learning, modern machine learning. So I don't know. It's a natural question arises: what is the ideal mini batch size? What size to choose for your mini batches. And again, there's no general answer, because that's a hyperparameter that you choose and you see how the loss function evolves. But the smaller the batch size, the better. In fact, he suggests that it's not here, but then in one of his Twitter posts, he suggested that the ideal batch size is 1, which is stochastic gradient descent. But again, it's slow. So there's this plot. There's this table from this paper, 2003 paper, which does this sensitivity analyses where the learning rates are varied, or for a given learning rate, you use different batch sizes and you estimate the accuracy of your training of your model of your trained model. And then what you see here is that for any given learning rate, for instance 0.1 here, using a batch size of 1,000 gives you an accuracy of 84.13 on this specific data set. We don't have to worry about what data set it was. But then for each learning rate, as you increase the batch size, your accuracy decreases. And then again, the highest accuracy for any given learning rate is when you use a batch size of 1. So I'm just trying to justify that, a small batch size is preferred over the whole batch. So always use mini batch gradient descent and have a small batch size. Now this is the final slide. And what this relates to is the error. I mean, when you're training your model, you want to track the error, as in how your overall loss function evolves as your model trains over multiple epochs or multiple iterations. Now, with any model, there's a possibility of underfitting or overfitting. Overfitting is where your model performs great on the values that you trained it on. But then if you train it on out of set data that it was not trained on, it performs very poorly. The loss is bad. So it's not generalizing. Now you see something like this as Gibbs phenomena as well in numerics, where you can use a higher order polynomial to approximate some data points, but then you get massive error on the edges. So ideally what so suppose this is a characteristic curve. You start to compute you start model training, you track loss over multiple epochs, but that's multiple iterations. And then your loss curve, the training loss evolves quickly, it decays rapidly, and then it, initially it decays rapidly, but then the decay is slower. But then if you test it on your testing data set, then you'll see that for certain initial epochs, your validation is decaying rapidly. But then after a while, the validation error starts to again increase. So that's the point where you want to stop your training. Okay. So again, you might ask, how do I know when to stop training? How do I know that the model is trained enough? This is the point. So this orange curve is famously known as the U curve because it looks like a U, and it essentially suggests that stop somewhere here where you are towards the minimum of the U. Okay. So this increases the generalizability of your model so that it performs well on the new data samples it has not seen during training. Now let's code. Assuming that, as you mentioned, we're able to install PyTorch on your laptop. I've added the Jupyter notebook for today's lecture in this link here, and just if you can access it, just let me know if that works for you. On the program website, this is a Google Drive link. It's not on the program website, but we can add it later. So for today, we will create an artificial neural net, a very simple artificial neural net that accomplishes this handwriting digit recognition task. Okay, and we will we'll try to create a neural network that has one input layer, one output layer, which tells you the prediction, and then 3 hidden layers. Okay, is everyone able to access the notebook? You'll have to download it and open it. Okay, so is there anyone who has not been able to download it or open it? Okay, good. So, so again, we start by loading in the necessary libraries. We just load NumPy and Matplotlib, that's standard. And then we import the torch library, the PyTorch library, and then we import the NN module as NN, and then we import the optimizer module as optimizer. And then again, these will allow you to randomly create random samples or random mini batches out of your samples that we download. And then there's this command which loads Torch Vision. So Torch Vision is a part of Torch, which provides you access to all the benchmark data sets and state-of-the-art data sets that are available for you to train your model on. Now, I don't have a GPU here, but if you want to train your model on GPU, this is the way to go. You first check if a GPU is available on your device. And then if isCUDA is true, then you set the device to a GPU. Otherwise, you continue to train your model on a CPU. Okay. So what we want to do is the following. We'll first load the data using Torch Vision commands, and then we'll prepare the data by creating mini batches. So this is a standard procedure which you will end up following whatever model you create. So then we will create a class that defines a neural network, that initializes the neural network, and then it defines how the forward pass is implemented in the neural network. Okay. And then, we'll do some hyperparameter setting and initialization, and we'll define the optimizer, the loss function. And then finally, we'll define a function that trains the model. which we created in step 3. And then finally, we'll train the model. Okay. So now Torch Vision allows you or provides you access to different kind of state-of-the-art data sets. So you can see some of them here if you just execute this command. Now, I don't know, are you able to execute the commands fine? Okay, good. So, I mean, there's tons and tons of data sets to choose from, but then some of the famous ones are the ones I mentioned here. So we'll use the MNIST data set, which is a set of 60,000 training samples that train on 28 by 28 pixels of handwritten digits. Okay. And then you have the CIFR 10 data set, which is a set of images, or I think it's animals. So there's 10 class of animals in there, and you can train your neural net to identify, between these 10 different classes of animals. And then similarly, the CIFR 100, which 100 represents 100 classes to train on and identify from. And then there's ImageNet, which is probably one of the biggest data sets out there. There's probably 14 million images. It was created at Stanford back in the 2000s by Fei Li and her lab. And then similar to MNIST, there's this fashion MNIST data set, which has pictures of, T-shirts, apparel, shorts, and all that. And then similarly, there's a data set for food, 101 food categories. So we'll hide this for now. And then PyTorch also allows you access to some pre-trained models that have performed very well in competitions, or are very well known to have great accuracy. So some of them are listed here, like AlexNet, and I don't know, Google LayNet, and there's some for vision transformers. So we will not use a pre-trained model today. We will create our own model. So this is just for your reference. So okay, we'll load the data set. So this cell here allows us to load the, can I hide this window? Does anyone know how to go full screen? Okay, so never mind. So the way you load the data set using the dataset utility command is this. So you execute this command. Root is where the command, where the dataset will be downloaded if it's not already there in your laptop. Train true means you will use it as a training dataset, and download true means download it if it's not already available. And then transform, which is part of the Torch Vision library, allows you to perform some rudimentary transforms on your data before training. So here I give you 2 examples of transforms. So first is transform to tensor in this list, which converts all the images you load into a tensor. Okay, that's necessary, as you can't use NumPy arrays in PyTorch to train. You will have to convert it to tensors. Then you are converting the image to grayscale. You might know that usually images have 3 channels, red, green, and blue. And then your final image is a combination of those 3 channels. So we are working with black and white images today. So we don't have to worry about that. And then you can add random rotation to your images to enhance generalizability of your model. Then you can add Gaussian blurring tools. And then I add list of some other transforms you can check, like resizing, cropping your image from the center. But then for now, we will just use a simple transform. That is, we convert our images to a tensor. Now, once you have, so you do this for training set, and then you do similarly for the test set. The 2 commands are identical, but then they only differ in a sense that you have set train to false, which indicates that you will use it to train, to validate your model after the training process during inference. So you can, it's a list. You get a, oh, okay, I should also execute the commands. So you, oh no, how much time do I have, Jim? 15, 20 minutes. Yeah. Okay. So now that you have your data sets loaded, your test set and your training set loaded, you can just see, you can print the pointers to the list of samples and see that it has 60,000 samples. So it has 60,000 images that you can train on, where numbers vary from 0 to 9. And similarly, you have 10,000 samples to test on. Okay, so we'll just visualize your random samples from your training set, and just creating a random number from 0 to 60,000, and then I'm just plotting what I get. So you can see, that's what our training set looks like. It's just numbers, black and white numbers, and this is the output label you get from the data set when you load it. Okay, so that takes care of step 1. Now step 2 is creating mini batches out of this training data. Okay, and then so you choose a random batch size. So you're dividing your 60,000 samples into small batches of 40 samples each, and then you're creating pointers, or again a list of many of these mini batches using the data loader command, which is offered by the torch.utils module. So you pop in the list of the training set samples, you set the batch size, drop last, you can set it to false, which is recommended, because that means that if you had, say, 251 samples and you have batch size of 40, then your last batch will have 11 samples. So you don't want to waste that. So drop last equal to false takes care of that. Shuffle equal to true. Whenever you train the model, it shuffles the samples. Okay, which is ideal, I guess. You do similarly for the test loader. So now after you execute this command, you get objects, you get data loader objects, which contain a list of mini batches, okay, that you will load during the training process. Now, if you want to iterate these data loader objects, you can use the iter command. Okay, you can use the iter command, and then that points out gives you the pointer towards your data set, and then you can use the next command to iteratively look at these samples. So this is what we are doing here. We are loading the samples using the next function and then plotting them. Okay. So now your data set is ready, and then now what you have to do is create the definition for your neural net. Okay, so far so good. I mean, this is kind of the boring part, I agree. This can vary from problem to problem, how you load your data set, where you load it from, how you shuffle it, and all that. But here's the part that is central, that will be similar to all the kind of models you create. So PyTorch offers the NN module base class, which you can which you can use to create derived classes which define your PyTorch model. So for instance, here you're using the NN module base class to create another class called ANN for artificial neural nets. Okay, so NN.module comes with two basic functions. That is the init function, that is the initializer function, and the forward function, which does the forward pass. Okay, so here in the init function, you first initialize all the members of the parent class using this function. It's a necessary function, because if you don't initialize your parent class properly, you might not be able to use all the features of the parent class. And it also allows multiple inheritance in some cases. So now we had a linear, now let's go. So suppose we have a neural net where this is the input layer, this is the first hidden layer, this is the second hidden layer, this is the third hidden layer, and this is the output layer. So you need 4 set of weights, or 4 set of affine transformations, which is connecting the first and second layer, second and third layer, third and fourth layer, and fourth and fifth layer. Okay, so the weights here are initialized using the nn.linear function. So you are introducing a linear transformation, and the first variable is the input dimension, like how many nodes you have, what is the size of input data. For our case, it would be 784, because 28 times 28, we will vectorize our image. And then we can randomly choose what the size should be. In this case, I've chosen the first hidden layer to have 128 dimensions. Okay, so then that goes next. And then you apply activation function. So once you have NN linear, that will do the affine transformation. But then to finally know the node values here during the forward pass, you need an activation function, as we saw yesterday. Okay, so that is done through this. You use an nn.relu function. Again, you can use one of the many activation functions that PyTorch offers. Now, ignore dropout for now. We can come to it if we have time. But this is a regularization technique. For now, just treat it as an identity function. It does nothing. Okay. Now comes the second layer. Second layer would be W2 here. So you again define your, that this had 128 layers. We are keeping this as 128 for now as well. So 128 values map to 128 values. Okay. And then again, you apply an activation function. And then you do something similar for the third layer. And then again for the fourth layer. And then finally the output layer. Okay. Yeah. So I think I have 64 here. And then we know there's 10 digits, 0 to 9. So our final output layer contains 10. So you have 64 mapping to R10. Okay. Now this is your initialization. You have initialized your function now. You have initialized your neural net. You have defined the architecture here. Now you define what happens when you do the forward pass. First you set the pointer to your own model, and then the input, which is the, this is X. So that's your input right here, the image. And then you first pass the image to the input layer, the first input layer. Then you pass it through the activation, and then the dropout, which ignore for now. And then it goes through layer 2, and then you apply the activation, second activation function, third layer activation, fourth layer activation, and then finally the output layer. So this is your forward pass. Your X is transformed to an output Y, and then this function ultimately returns that value Y. Okay. Now again, ignore this prune function. This is a technique used to improve your model output, but we can ignore it for now. But here's a trick. If you think that definition was complicated and you don't want to use it, then you can have you can use these the NN sequential function to just define your models in this fashion. So that's definitely easier than going through all these different steps. But the disadvantage is you won't be able to define your own customized forward function. The forward function is pretty much defined in this definition by PyTorch. Now again, now we have defined the model, how it looks like, what it will do in the forward pass. Now you want to set an optimizer and a loss function. So again, you can execute this command to see all the functions, all the optimizer functions. We discussed some of them: Autograd, Atom, and then SGD, stochastic gradient, RMS prop. Right? There are many others. So now you have the derived class for the neural net. So now you create an instance, an object of that class. So this will be our model. A model will be called digit identifier, and you initialize it like this. You can have some input arguments here to initialize your model, but for right now they are by default set. But that's an option. Okay. And then you define your optimizer using this optim.atom or optim.rmsprop or optim.sgd. And then the key hyperparameter you pass through while initializing the optimizer is the learning rate, the alpha term we saw before, okay, the step size that you take. And then you pass the model parameter, the pointer to all the parameters the model has, which is all the weights and biases, okay? So once you do that, once you create an object of the NN class, you will see that, So once you do that, you can look at the structure of your model, okay? It has all the layers that you defined, the linear layer, the activation function, and so on. Now, if you just want to know, so there could be a model evaluation mode and a model training mode. If you want to see what mode your model is in, you can just use this command .training. And when you create a model, it is by default in the training mode, which means when you do the optimizer.step command, it will actually update the parameters. If it's not, if it's in the evaluation mode, it will not. Now, we need to define a training function. Okay, so it's a simple function which takes the number of epochs you want to train it for, the model pointer, the optimizer you want to solve, used to update your weights, the loss function that you want to quantify your penalty, the training set, the pointer to your training set, the pointer to your test set, and the batch size. Again, most of these are necessary, but then you can always add more variables, arguments to the function if you want. Okay, so let's see what this function is doing. I mean, it's creating some arrays, random arrays to track the error. So, but this is the main part. For epochs, for how many iterations, how many big iterations your model is being trained for. So say a good number would be 10 to 20 to begin with. So if you train a model for 20 epochs or 10 epochs, for each epoch, you first set your model into training mode. That is, update the parameter if the optimizer changes it. And then for each of the mini batches, so this is, so, we created the data loader to generate mini batches. So you can extract or load one mini batch using this command, using the enumerate function. It pops out I, input and output. You convert the input, which is the image, into a 784 vector. And then you do the prediction using the model function. It's just a functional form. You put in the input in this command, you put in the input, the vector of images, and then it gives you the output y, output prediction y, okay? So that's what you have here. So now you have your prediction. Next, what you want to do, if you remember the 5-step process, you compute the loss or how far your prediction is to the truth. So that's what you do here, okay? Now, ignore this command. It's not doing anything relevant. It's just used for tracking. But this optimizer.0grad function, it sets all the gradients of the optimizer to 0 first. Otherwise, it just accumulates it every step. That's a core key property of PyTorch, okay? So this command is necessary. But then after that, you use the loss and then you do the loss.backward, execute the loss.backward command. And this computes the gradient with respect to all the model parameters. And finally, once your gradient is computed, you use the optimizer.step function to update your parameters. Okay. So, and then you can return some trackers to visualize what your training loss was. So now we train the model. This is the final step. So you set how many epochs you want to train the model for, and then you just use the training function by passing all the necessary pointers: epoch, model, pointer, optimizer, loss function, the train loader pointers. Okay, and now let's see what we get. Or actually, let's do this. Let's first do this. Let's set a large learning rate for Adam, and then train the model. Now it will pop out the prediction skill, that the model has achieved so far. Okay. This is taking forever. Okay, it's starting to show up. So you see, for the first iteration, the model skill is pretty poor. It's 10.28%. I mean, a baby can do better. And it's not improving, apparently. Any questions so far while the model trains? Yeah.
How do we determine the size of the hidden layers?
Yeah, there's no general answer to this. But usually, if you have a 784 vector, it's good to have something on that order, 784 long vector. So that's why it's just 128. Now, yeah, you don't want a very long hidden layer as well, because of the reason we discussed. You need more and more training data to train the model then, and it might not generalize better. So again, all this is an area of active research. So there was this paper recently this year, which introduces a new kind of optimizer called automatic gradient descent, where it uses some ideas from numerical optimization, and the way it updates your weights at every step is that your size of your hidden layer doesn't matter. So I mean, again, setting all these hyperparameters is kind of takes a lot of time, but I'm sure maybe 10 years from now we'll have better answers to these questions. But start small. That's a good general answer. So yeah, we see that the model doesn't really do anything because the step size is probably too large. Your learning rate is large, so the step size is it's just missing the right direction or the right. It's even if it's if this is your loss curve, and this is your initial position. It's supposed to go there, but because the step size is large, it's probably just going somewhere there and not able to find the optimal. Now let's try to change the learning rate, decrease the learning rate, decrease the step size. Okay. And once we do this, we will note that everything falls in place. The model skill suddenly jumps to a much higher value. So remember, during the first pass, our error prediction skill was like 10%, 11%, right? Not good. But you see, you decrease the learning rate, and then now your model skill is 95.92%. It's a sharp jump. And then it gets better with every epoch. So, I mean, I had a set of tests that I wanted to show, but I can just, tell you, and you're free to try it offline. So so now we have a better learning rate, 10 to the power minus 3 for Adam. Try switching the optimizer. Just try switching your Adam optimizer to, say, stochastic gradient descent with the learning rate constant. Okay. So when I tried it, I found that stochastic gradient performs very badly with that learning rate. Okay. Because it doesn't have those fancy things like momentum and all that, right? So those things actually heavily heavily help you train your model faster. And then, you can try different batch sizes. So I guess we can do that, and that could be the last test of the day. So you see the model skill is increasing. It started with almost 96, and then it's heading towards 98. And that's pretty impressive. I have to wait to be in the training. But the next step is kind of visualizing your error. You want to see how exactly your error evolved. Like, is your error sufficiently low, and how does your error compare to the validation error? So you remember that U curve we saw? You want to check that you're not overfitting your model and that everything seems right. And that's how you do it. I mean, by plotting the training curve, training loss alongside the validation loss. And I mean, if you're overfitting, then you'll see this orange curve heavily, starts to increase with more and more epochs. Now our model is trained, and then it was able to learn or obtain a prediction skill of 97.66%. So that's pretty impressive. And now you want to use the model for inference. So we want to see what kind of samples the model did perform badly on. Why did it make those wrong predictions? So we again load the data set, and then for each data set. So see here, the correct answer for this image is 9, but then it's predicted as 4, and you can see why. It doesn't really have that bar go all the way that usually goes in a 4, right? And then similarly, the correct answer is 8, but then the prediction is 3. This is pretty bad, actually. I mean, should have guessed it as 3, but I guess it's the loops that, if you cut 8 in half, you get a 3. So maybe it didn't learn that very well. So similarly, you can do this for all other, samples. Why is it not changing? Okay. Sorry. So then you can, look at other samples. The correct answer was 5, but it predicted as 3, and you can kind of see why. So it's like you use a simple model to create a digit identifier, but then you see that its performance sort of asymptotes at 98% or so. You can kind of play around with the model architecture, have more layers, less layers, and see how the performance varies. Okay. But tomorrow, what we'll do is because it's an image, instead of using an ANN, we'll use a CNN, which is built for image processing, and then we'll see that just using a different way of processing your input makes a massive difference to the prediction skill of the models, and we might even reach 99%. Now these state-of-the-art models have accuracy of 99.84%, which is again pretty impressive. But then, yeah, we are not really in that ballpark right now, but we'll get near. So yeah, I guess this would be a good point to stop. Or maybe we can do just one test before, and then we can can have questions in the meantime. So I just set the batch size as something large. Okay, so kind of moving towards batch gradient descent rather than mini batch gradient descent. Okay, we don't need this, but we have a batch size of 10,000 now. And this. Okay, so yeah, and again, I think I did not mention it, but when you are actually using your model to compute the training loss, it's important that you set the model to evaluate, because otherwise it can affect your model weights, and they are prone to change. But if you set it, if you run it in the model.training mode, but if you set model.eval or model.training to false, that the model is used for inference, then it does not affect your weights during this inference step. Okay, and let's see how it's performing. Okay, so you see it started with a very poor skill as opposed to when we used a small batch size of 40. But then at least, as opposed to having a bad learning rate, it's at least approaching a good impressive skill. So yeah, I guess that's we'll stop here today, but then we'll continue tomorrow and see how to build on this and develop CNNs.
Okay, so hopefully you all got used to some of the stuff. So we are running out of time, so we'll have a quick coffee break and come back at 4 o'clock. So